Right now, on the shoulder of the constellation Orion, there is a soft orange star that you have seen 100 times without ever learning its name. It is called Betelgeuse, and it has hung in that same spot through the whole of human history, reliable, familiar, apparently settled. But over the last decade, it has quietly become the most closely watched star in the sky, and every time astronomers point a great telescope at it expecting answers, it hands them stranger questions instead. It dimmed until it changed the shape of a constellation. It hid an entire companion star inside its own glare for 100 years. It spins at a speed that should be impossible. We cannot even agree on how far away it is, or how large it is, or how close to the end. And here is the question that should keep you here tonight. Why is it that the harder we study this one familiar star, the more frightening it becomes? And what exactly is it that we are so afraid to find? Get comfortable and settle in. If you are the kind of person who finds it quietly thrilling to watch something familiar turn strange, a slow like and a subscribe help this channel reach more curious minds like you. Because by the end of tonight, the soft orange star on the hunter's shoulder is going to feel like something else entirely. Now, let's slowly settle into the dark. There is a star you already know, even if you have never once said its name out loud. On any clear winter evening, if you step outside and look toward the south, you will find 3 bright points in a short, straight row. That row is the belt of Orion, the hunter, and it is one of the oldest pictures that human beings have ever agreed on. Cultures separated by whole oceans and thousands of years looked up at that same little row of stars and drew the same broad shape around it. A figure, standing, with a belt at the waist and a raised arm, and at the top of that raised arm, on the hunter's right shoulder, there is a single star that glows a soft, muted orange, different from all the cold white and blue points around it. That star is Betelgeuse. Tonight I want to sit with it for a while, because it is one of the strangest objects we can point to, and because the closer we look at it, the less we seem to understand. For most of human history, Betelgeuse was simply there. It was reliable. It was the warm-coloured corner of a familiar shape, one of the 10 or so brightest stars in the entire sky, and from most of the northern half of the world it ranks even higher than that. If you have ever noticed a single reddish star hanging in the winter dark and wondered, without really asking, what it was, there is a very good chance you were looking straight at it. Sailors used it. Ancient astronomers catalogued it. Its very name is a worn-down fragment of an old Arabic phrase, something close to the hand, or the armpit, of the giant, passed through so many centuries and so many translations that the original words have almost dissolved. You may even know it, without knowing you know it, from the way its name was borrowed and twisted for a certain black and white ghost in a striped suit. The star has been sitting quietly in our collective memory for a very, very long time, and that is exactly the feeling I want you to hold on to as we begin, because we're going to spend the rest of our time together taking it apart. That sense of familiarity, that comfortable certainty that this is a known thing, a settled thing, a fixed point that our ancestors saw and our descendants will see, unchanging, in the same corner of the same constellation. It feels permanent. It feels understood. When something has hung in the same place in the sky for the whole of recorded history, it is almost impossible not to assume that we have it figured out, that the astronomers long ago measured it and filed it away and moved on to harder problems. The truth is close to the opposite. Betelgeuse is not a solved problem. Over roughly the last decade, it has quietly become the single most closely watched star in the entire sky, and it has earned that attention by refusing again and again to behave the way our models say it should. Every time a team of astronomers has pointed a great telescope at it and expected to close the book on some question, the star has answered by opening 2 new questions in its place. It has dimmed when it should have held steady. It has hidden things from us that were sitting in plain sight. It has spun in a way that should be impossible. It has changed its apparent size and its apparent distance depending on who is measuring and how. And underneath all of that, it is running an invisible clock that none of us can read. So here is the strange promise of tonight. I am not going to tell you that Betelgeuse is about to hurt you, because it is not, and I will explain very clearly why not before we are finished. What I am going to show you is something quieter and, in its own way, more unsettling. I am going to walk you through the last several years of studying this one star discovery by discovery, and I want you to notice a pattern as we go. The pattern is that the more carefully we look at Betelgeuse, the scarier it gets. Not because it grows more dangerous, but because it grows less knowable. Each new answer makes the star feel less like something we understand and more like something we're only guessing at, standing underneath and squinting up at a light that left it centuries ago. By the end of tonight, you will understand exactly what that means. You will know what happened when Betelgeuse began to fade in front of the whole world. You will know about the companion that was hiding inside it, unseen for 100 years. You will know why its spin should not be possible, and why we're not even certain it is spinning. You will know what is happening right now, this very second, in the part of the star we can never see. And you will know what it will look like on the night it finally dies, and why that death, when it comes, will be the most beautiful thing our sky has offered in the whole span of human memory. But we're getting ahead of ourselves. To feel how far the star has drifted from that comfortable, familiar shoulder, we have to go back to the night the familiar thing first went wrong. In the last months of 2019, a handful of astronomers began to notice something that, at first, they almost did not trust. Betelgeuse was getting dimmer, not dramatically, not all at once, but steadily, week after week, in a way that did not fit its normal habits. Now, this is a star that changes brightness all the time. It is what astronomers call a variable star, meaning it swells and shrinks and brightens and fades on a rough rhythm, the way a chest rises and falls with breathing. Small dips were nothing new, but this dip did not stop. Through December and into January of 2020, and on into February, the star kept fading, further and further, past any level anyone had recorded in more than 100 years of watching it carefully. By the bottom of it, around the middle of February 2020, Betelgeuse had lost roughly 60% of its usual brightness. It had fallen to something like 40% of its normal light. To put that in plainer terms, one of the brightest stars in the sky had faded until it was noticeably, visibly dimmer to the naked eye. And here is the part that made it feel almost eerie. Because Betelgeuse is not just any star, but a specific corner of a specific and deeply familiar shape, the dimming actually changed the way Orion looked. The hunter's shoulder had gone dark. People who had known that constellation their whole lives stepped outside, looked up, and felt that something was subtly, unmistakably off, even when they could not immediately say what. The picture in the sky that had looked the same for 40,000 years suddenly did not. It is worth appreciating just how carefully this star has been watched, because that is what made the dimming so undeniable. Betelgeuse is one of the most monitored variable stars in the sky, followed not only by professional observatories, but by a worldwide community of dedicated amateur astronomers who measure its brightness night after night and have done so for well over a century. Their patient records stretch back generations, a long, unbroken ledger of how bright the star has been on thousands of nights. That is why the great dimming could be stated with such confidence. It was not one person's impression that the star looked faint. It was a clear departure from a century of careful measurement, a fall to a level that the long record had never shown before. When you have that much history on a single star, an event that breaks the record cannot be waved away. And the story did not end at the bottom of the dip. After reaching its minimum in early 2020, Betelgeuse recovered. Over the following months it brightened back toward its normal levels as the cloud of dust it had ejected thinned and dispersed and drifted away, clearing the veil from its face. The star climbed back to something like its usual brightness, and the immediate alarm faded with the dust. But then, in the years that followed, Betelgeuse did something else that kept the attention on it. At times it brightened beyond its normal levels, glowing brighter than its long-term average, and each time it did, the old question stirred again in the background. The star had shown everyone that it was capable of dramatic, record-breaking changes, and having seen that once, no one was quite willing to look away again. The dimming had not answered the question of Betelgeuse. It had only made the whole world start watching, and once the world was watching, it could not unsee what the watching revealed. The dimming was the door. Everything that followed, the hunt for the cause, the discovery of the companion, the argument over the spin, the reappraisal of the distance, all of it flowed from that first strange fade, as if the star had cleared its throat and, having gotten our attention at last, proceeded to show us just how little we had ever really understood about it. You can probably guess the question that followed, because it is the same question that has hovered over this star for as long as anyone has understood what it is. Was Betelgeuse about to explode? This is a star that everyone in astronomy knows is going to end its life as a supernova, a colossal explosion at some point. So when it started doing something it had never been seen to do before, when it began to fade in a way that broke a century of records, a very natural and very human thought spread quickly. Maybe this was it. Maybe the fading was the star faltering, the first flicker before the end. Maybe we were watching, in real time, the opening moment of the death of Betelgeuse, and any night now the sky would tear open. The idea caught fire far beyond the astronomy community. It spilled into news headlines and into ordinary conversation. For a few weeks in early 2020, a surprising number of people who had never thought about a red supergiant in their lives were suddenly checking on the health of a specific star on the shoulder of Orion, watching it the way you might watch a candle guttering low. There is something revealing in how fast that worry spread. It tells you how deeply we assume the sky is stable. The alarm was not really about danger, because most people had no clear idea whether an exploding star could even reach us. The alarm was about the wrongness of it. A fixed thing was moving. A permanent thing was changing. The corner of the picture was going out. And this is the first turn I want you to feel because it sets the shape for everything that comes after. The dimming of Betelgeuse was frightening precisely because it violated our sense that we understood the star. We had filed it away as reliable, and it was misbehaving. But notice what the fear assumed. The fear assumed we knew what the dimming meant. It assumed that a fading star must be a dying star, that the dip in brightness was a message we could read, a countdown we could interpret. That assumption felt obvious. It felt like common sense. A star grows dim, the star is in trouble, the end is near. And that assumption, as we were about to learn, was almost entirely wrong. The real explanation would turn out to be stranger than the fear, and it would be the first in a long line of answers that each solved one mystery only by handing us a larger one. Because when astronomers finally worked out what had actually dimmed Betelgeuse, the relief they felt came wrapped around a new kind of unease. The star had not been dying. But what it had actually done was, in its own way, harder to sit with. It had thrown a piece of itself into space. To understand what that means, and why it should trouble us more than the explosion we feared, we have to look very closely at the surface of a star that is so large and so turbulent that the word surface barely applies. Here is what the great telescopes eventually revealed. In the year or so before the great dimming, Betelgeuse did something violent. It ejected a piece of its own surface, an enormous bubble of hot gas, an amount of material that is genuinely difficult to hold in the mind, tore loose from the star and drifted outward into space. As that bubble expanded and moved away, it cooled. And as it cooled, the gas in it condensed into dust, fine grains of solid material, forming a kind of dark cloud. That cloud drifted across the part of the star that faces us, and it blocked a large fraction of the star's light. From our vantage point, hundreds of light years away, the star appeared to fade. But Betelgeuse itself had not dimmed in the way a dying ember dims. It had partly hidden behind a veil of its own making, a shroud of dust it had coughed up from its own body. Astronomers have a technical name for this. They call it a surface mass ejection. Our own sun does something distantly related when it releases what are called coronal mass ejections, great belches of charged particles that occasionally sweep past the Earth and light up the polar skies. But the event on Betelgeuse was not a cousin of a solar flare so much as a monster of an entirely different scale. The best estimates suggest that the amount of material Betelgeuse threw off was on the order of hundreds of billions of times the mass of a typical ejection from the Sun. The star did not have a bad day. It tore a chunk out of itself large enough to cast a shadow across its own face, a shadow we could see from the far side of 500 light-years of empty space. Let me try to put you there, because the numbers alone will not do it. Imagine you are hanging in space close to the surface of Betelgeuse in the months before the dimming. There is no clean surface here the way there is on a planet. Beneath you, the star is not a solid ball, but an ocean of glowing gas, and it is not calm. The surface of Betelgeuse is not covered in millions of small features the way the Sun's is. Instead, it heaves with only a handful of titanic cells, each one a bubble of plasma rising and falling, and a single one of those cells can be as wide across as the distance from our Sun to one of the inner planets. You watch one of these enormous cells swell upward beneath you. a slow, seething dome of orange fire larger than a world, larger than many worlds. The gas piles up, something gives, and then a section of the star's outer layer simply lifts away, peeling off into the dark, a continent of star stuff the size of the inner solar system rising and separating and beginning its long drift outward. As it climbs away from the heat, it dims from blinding orange to dull red to nearly black, and the fine grains of dust begin to form inside it, and that drifting, cooling, darkening cloud is the thing that, months later and light years away, will make people on a small blue planet look up and wonder if their star of winter is about to die. Now sit with what that actually tells us. The good news, the reassuring news, is that Betelgeuse was not exploding. It had simply had a convulsion, a shudder, and thrown off a piece of itself, and the fading was a trick of dust and geometry, rather than a death rattle. That is genuinely comforting. But look one layer deeper and the comfort thins out. Because what we learned was that this star can, without any warning we know how to read, hurl an amount of its own material into space that beggars comparison, in an event so large we could watch its aftermath from the other side of the galaxy's local neighbourhood. This was not behaviour our tidy models of a red supergiant cleanly predicted. The dust itself is worth a thought because it is a small clue to something much larger. The grains that formed in the ejected cloud and veiled the star are made of the very elements the star has been forging in its layers, heavier atoms condensing into fine solid particles as the gas cooled, the same basic kinds of grains that drift through space and one day gather into new worlds. In throwing off that shroud, Betelgeuse was doing, on a visible and dramatic scale, a gentler version of the thing that all such stars do throughout their late lives. They shed material steadily into space, seeding their surroundings with gas and dust, enriching the space around them long before the final explosion ever comes. Betelgeuse is losing mass all the time, breathing pieces of itself out into the dark, and the great dimming was simply the most spectacular single instance of a process that never really stops. What that tells us is that the star is not a sealed, static object quietly waiting to explode. It is leaking, venting, convulsing, actively reshaping the space around it right now, in ways we can watch. And each of those convulsions is a small reminder of how much energy is churning just beneath that deceptively soft orange glow. When you look at Betelgeuse and see a calm point of light, you are seeing the smoothed-over surface of something in a constant state of upheaval, a star that is dying not in a single future instant, but in a long, restless, ongoing process that has been underway for a very long time, and that occasionally, as in 2019, breaks through into something we can see with our own eyes from hundreds of light-years away. It was the star showing us that it is more restless, more unstable, and more capable of sudden extremes than we had assumed. We went looking for the cause of a dimming, and we found a star that can spit out worlds. It is worth pausing on just how alien the surface of Betelgeuse really is, because it is the source of so much of the trouble. When you picture the surface of our own sun, you should imagine something almost fine-grained. The sun's visible face is covered in millions of small cells of rising and sinking gas, each one about the size of a country, packed together like a floor of shimmering tiles. That fine, even texture is part of why the sun is, for all its power, a fairly well-behaved and predictable star. Betelgeuse is nothing like that. Because it is so enormously swollen and so much cooler, its outer layers organize themselves into only a handful of gigantic convection cells, perhaps just a few of them covering the whole visible face at any given time. Each single cell is a bubble of plasma so large that it could hold the orbit of an inner planet inside it. These few monstrous cells rise and burst and sink on their own slow schedule, and as they do, they change the brightness and even the apparent shape of the star from one stretch of months to the next. This is why so many of the measurements we have discussed come out fuzzy and disputed. A star with a few enormous shifting hot and cold patches does not present a clean, steady face to measure. Its centre of brightness wanders as the cells churn. Its edge is soft and restless rather than sharp. When you're trying to detect something as delicate as a tiny wobble in position or a faint companion in the glare, a surface that reshapes itself every few months is close to a worse case. And the surface mass ejection we have just described almost certainly grew out of this same violent convection. A cell of extraordinary size welled up, the outer layers above it lost their grip, and a piece of the star lifted away. The dimming was not a special one-off catastrophe visited on the star from outside. It was the natural, if extreme, behavior of a body whose surface is a slow, seething, world-sized boil, and that realization is exactly what should give us pause. The star is not misbehaving. This restlessness is simply what Betelgeuse is, and this is where the pattern I promised you first shows its face. We asked a simple question. Why did Betelgeuse grow dim? We got an answer. It ejected a piece of itself and hid behind the dust. But that answer did not close the book. It opened a new and larger question. What kind of star does that? And how little do we really understand about what is happening beneath that churning, ejecting surface? Every answer opened two more questions. Hold that phrase in your mind, because we are going to hear it again and again tonight, and each time it returns it will carry a little more weight. For now, we turn to a second mystery, one that is older than the dimming, one that had been quietly puzzling astronomers for an entire century, hiding inside the star's rhythm like a second heartbeat nobody could explain. For as long as astronomers have watched Betelgeuse closely, they have noticed that it breathes on more than one rhythm. The main pulse is a little over 400 days long. Over roughly that span, the star swells and brightens and then shrinks and dims, a slow, steady heartbeat driven by the physics of a giant star's outer layers expanding and contracting. That much made sense. Many pulsating stars do something similar, and the 400-day rhythm fit reasonably well with what we understand about a star of Betelgeuse's size and temperature. It was the tidy part of the picture. But sitting underneath that main pulse was a second, much slower rhythm, and this one nobody could explain. On top of the 400-day breathing, Betelgeuse showed a longer cycle, a gentle rise and fall in brightness that repeated roughly every 2100 days. That is close to 6 years. 6 years for a single slow swell and fade, layered over the faster 400-day pulse like a long tide moving underneath ordinary waves. Astronomers had a rather deflating name for this kind of pattern. They called it a long secondary period, which is really just a label that means a slow variation we have measured but cannot account for. It is one of the oldest unsolved puzzles in the study of red giant and supergiant stars, and Betelgeuse wore one of the clearest examples of it. And Betelgeuse is not alone in this. Long secondary periods show up in a large fraction of pulsating red giants and supergiants across the sky, hundreds and hundreds of them, and for decades astronomers have offered one idea after another to explain the phenomenon in general. Perhaps it was some slow oscillation in the star's outer envelope that our physics did not properly capture. Perhaps it was great clouds of dust forming and clearing on a cycle. Perhaps it was enormous convection patterns turning over on a long rhythm. Perhaps in some cases it was a companion. Every explanation could account for some of the stars but not all of them, and the puzzle stubbornly refused to resolve into a single clean answer. This is worth knowing because it tells you that the strangeness of Betelgeuse is not entirely unique to Betelgeuse. It is an especially bright, especially close example of a mystery that hangs over a whole class of dying stars. When we struggle to explain the slow heartbeat of this one star, we are really bumping up against a gap in our understanding of what happens in the bloated outer layers of all aging giants. Betelgeuse simply happens to be the nearest and clearest window onto that gap, which is exactly why solving its particular rhythm mattered so much. If we could explain the 6-year pulse of the one supergiant we can see best, we might finally have a handle on a riddle that spans the sky. Think about how strange that is. This is the brightest and most studied red supergiant in the sky. It is close enough that we can, with the best instruments, actually begin to make out its disk, rather than seeing it as a single point. Generations of astronomers had poured attention into it, and yet the star was keeping a slow, steady rhythm, a 6-year swell that anyone with a long enough record could measure plainly, and we did not know what was causing it. The heartbeat was there in the data, clear as anything, and its source was a blank. For about 100 years, a suspicion had drifted in and out of the scientific conversation about what might be responsible, but it had never been confirmed, and it had never quite gone away either. That suspicion was this. What if Betelgeuse was not alone? What if there was something else there? Another body, a companion, orbiting the great star and tugging on it, or passing through its light on a 6-year cycle? And what if that companion was the hidden hand behind the slow rhythm? It is a natural idea because a great many stars in our galaxy are not single stars at all but pairs, 2 stars bound together, circling a shared centre. If Betelgeuse had a partner, an unseen companion moving around it once every 6 years or so, that could, at least in principle, explain the long secondary period. The rhythm would not be the star breathing on some mysterious inner cycle. It would be the footsteps of something circling it. There was only one problem with that beautifully simple idea. Nobody could find the companion, and it was not for lack of trying. Astronomers pointed our finest instruments at Betelgeuse, including telescopes in space precisely to hunt for any second point of light near the giant. They came up empty, over and over, and you can understand why. Imagine trying to spot a single firefly hovering right next to the beam of a lighthouse from miles away. The overwhelming glare of Betelgeuse, one of the brightest stars in the whole sky, would drown out anything small and faint sitting close beside it. If a companion was there, it was buried in the light of the giant, lost in the glare, tucked so close to that blazing shoulder that our sharpest eyes slid right past it. And the guess was natural for a good reason, because companionship is the ordinary condition of stars, not the exception. When we look out at the stars of our galaxy, a very large fraction of them turn out to be not single stars at all, but pairs, or even triples and larger families, 2 or more stars bound together and circling a shared centre of gravity. Our own Sun, alone with its planets, is in some ways the odd one out. Massive stars in particular, the big, bright, short-lived kind that Betelgeuse belongs to, are especially likely to be born with siblings close beside them, because the great clouds of gas that form such stars tend to fragment and produce several at once, near neighbours from birth. So when astronomers noticed an unexplained rhythm in Betelgeuse, reaching for a hidden companion was not a wild leap. It was the most reasonable first guess, the explanation that fit the general habits of stars like this one. What made it maddening was simply that the guess could not be confirmed. A perfectly plausible companion, exactly the sort of thing that should be common for a star of this type, sat there as a leading explanation for a century, and yet every attempt to actually see it failed. The idea was sound, the evidence was missing, and that gap between a reasonable expectation and an actual observation is a theme that runs through the whole study of this star. We could reason our way to what ought to be there. We just could not lay eyes on it, which is exactly why finally catching the companion, when it happened, felt less like a surprise and more like a long-held suspicion at last being dragged into the light. The suspicion lingered for a century, plausible and unproven, a ghost in the data that we could measure but never see. And that is the state the mystery was in when the modern Death Watch began. A slow, 6-year rhythm with no confirmed cause. A century-old guess about a companion that no one had ever managed to lay eyes on. It would have been easy to assume the guess was simply wrong, that the rhythm came from some quiet complexity in the star itself, and that there was nothing else out there to find. But that assumption, like the assumption that the dimming meant death, was about to be overturned. Because in the span of a single remarkable year, using a clever trick to defeat the glare, astronomers were going to do something 100 years of trying had failed to do. They were going to find the thing hiding in the light, and what they found would be a whole star that had been sitting there, unseen, the entire time. In July of 2025, a team of astronomers announced something that a century of searching had never achieved. They had most likely actually seen Betelgeuse's companion, not inferred it, not deduced it from a rhythm in the data, seen it as a faint separate point of light sitting right beside the giant. To do it, they had to outsmart the very thing that had defeated everyone before them, the blinding glare of the star itself, and the way they did it is worth understanding, because it tells you how hard won this discovery was. The team used one of the large telescopes on a mountaintop in Hawaii, an instrument with a main mirror a little over 8 meters across, and they paired it with a special technique called speckle imaging. Here is the idea behind it. When you look at a star through a telescope, the Earth's atmosphere is constantly shivering and rippling, and that shimmer smears the star's image into a blurry blob. It is the same effect that makes stars appear to twinkle. Ordinarily, that blur limits how fine a detail you can see, and it is part of what had hidden the companion. But speckle imaging beats the blur with speed. Instead of taking one long exposure and letting the atmosphere smear it, the instrument takes thousands of extremely short snapshots, each one lasting only a small fraction of a second, fast enough to freeze the atmospheric shimmer in place. Then, with careful processing, those thousands of frozen instants can be combined to reconstruct an image far sharper than the shivering air should allow. It is a way of reaching through the atmosphere and pulling out detail that even telescopes in space had missed. And the timing of the observations was the clever part. The team did not simply look once. They had looked at Betelgeuse back in 2020, and at that time, based on the predicted 6-year orbit, the companion should have been on the far side of the giant, hidden behind it from our point of view. And in those 2020 images there was nothing. No companion. Then they looked again in late 2024, at a moment when the companion, if it existed, should have swung out to its widest separation from the star, as far to one side as it ever gets. And this time, in the 2024 images, a faint point of light appeared, sitting just beside Betelgeuse, exactly where a companion at its widest separation ought to be. The thing was there when the orbit said it should be visible, and gone when the orbit said it should be hidden. After 100 years, the ghost in the data had a face. I want you to slow down here, because this is the first moment tonight where I think the real weight of the thing lands. For a century, this companion was there. It was orbiting Betelgeuse the entire time, once every 6 years, moving through the outer layers of the giant, circling that famous shoulder, while every astronomer who ever studied the star looked straight at it and saw nothing. It was there when the star was catalogued. It was there through every measurement, every photograph, every careful study. A whole star, something on the order of 1.5 times the mass of our sun, was hidden in plain sight, tucked so close to the giant that its light was simply swallowed, and we did not know. We had no idea. The single most watched star in the sky had a companion buried inside its glare, and it took a special trick and a century of failure before we finally caught it. Now let that thought turn around and point at everything else. If we could miss an entire star sitting right next to the one object in the heavens we watch most closely, then what does that say about how well we truly know Betelgeuse itself? Familiarity, it turns out, is not the same thing as knowledge. We had been looking at this star for all of human history, and we had not even counted how many stars we were looking at. The companion earned a name. The astronomers proposed calling it Siwaha, from an Arabic phrase meaning her bracelet, a lovely choice given that Betelgeuse itself carries that old name meaning the hand of the giant. A bracelet circling the hand, and the details they could tease out of that faint point of light only deepened the strangeness. The companion appears to be a young star, hot and small, roughly the size of our sun or a little larger, and here is the surprising part. Many people had assumed that if Betelgeuse had a companion, it might be a dead star, a burned-out cinder like a white dwarf or a neutron star. Instead, this looked like the opposite, a young star that had barely gotten started, still settling into its life, and its orbit is astonishingly tight. It circles only about 4 times the distance from the Earth to the Sun away from the giant, which is closer than Jupiter orbits our Sun. But Betelgeuse is so enormously swollen that this orbit actually runs through the star's own outer atmosphere. The companion is not orbiting cleanly in empty space. It is ploughing through the thin, extended outer layers of the giant once every 6 years, like a swimmer moving through the shallows. And that detail led, only months later, to the confirmation that removed nearly all doubt. In January of 2026, a separate team using the Hubble Space Telescope, together with observations gathered over nearly 8 years, found the companion's fingerprints in a new way. As the little star ploughs through Betelgeuse's outer atmosphere, it leaves a wake, a trail of dense gas stirred up behind it, in the same way a boat leaves a churning trail as it moves through water, and that wake, the astronomers found, appears right on schedule, just after the companion crosses in front of the giant every 2100 days. There it was. The 6-year rhythm that had gone unexplained for 100 years was the companion, circling, ploughing, trailing its wake through the giant's atmosphere, stirring the star and shaping its light. The century-old guess had been right all along. There is more to the companion's story, and it only sharpens the strangeness. Because Siwaha orbits so close that it passes through the outer atmosphere of the giant, it is not moving through clean, empty space the way a distant planet orbits a star. It is dragging through gas, and dragging costs it energy. Over time, that steady friction is expected to rob the little star of its orbital momentum and cause it to spiral slowly inward, closer and closer to the giant, until at last it is pulled all the way in and swallowed. The companion is very likely doomed. It is expected to merge with Betelgeuse, to be devoured by the very star it circles, possibly before the giant itself explodes. And this connects to something we will come back to shortly, because one of the leading ideas for why Betelgeuse spins so strangely fast is that it swallowed a companion in the past. If that is true, then we may be watching the setup for a repeat, a star that has eaten before and is slowly reeling in its next meal. Astronomers already have their next test circled on the calendar. The companion's orbit brings it out to its widest separation from the giant roughly every 6 years, and the next time it should swing out far enough to be caught again is predicted for late in 2027. That is when the great telescopes will turn back to Betelgeuse and try to confirm the companion a second time, to firm up its mass and its orbit and its nature, to move it from a probable detection to a certain one. Until then, Siwaha sits in that uncomfortable middle ground that so much of this star occupies, almost certainly real, traced by its wake and predicted by its rhythm, but still just shy of absolute proof. A whole star, discovered and yet not quite pinned down, hiding in the light of the most watched star in the sky. But solving that mystery, as always with this star, did not calm things down. It simply moved us on to the next impossible thing, because the very same techniques that were revealing the companion were also confirming something about the giant itself that should not, by the rules of physics as we understand them, be true at all. Every star spins. Our own sun turns on its axis roughly once a month. Stars are born spinning, out of collapsing clouds of gas that carry a swirl with them, and they carry that rotation through their lives. So it is no surprise that Betelgeuse should spin too. The surprise is how fast it appears to be doing it, because the speed astronomers have measured is not just a little higher than expected. It is impossible. It breaks the rules of how we understand a star like this should behave. To measure a star's spin, astronomers use a subtle effect. When a star rotates, one edge of it is turning toward us, and the other edge is turning away. The edge coming toward us has its light shifted very slightly toward the blue end of the spectrum, and the edge moving away is shifted very slightly toward the red. In the same way, the pitch of a siren rises as it approaches and drops as it passes. By measuring that shift across the face of the star, you can read off how fast it is turning. Using a great array of radio dishes in the high desert of Chile, astronomers measured the gas around Betelgeuse and found an equatorial rotation speed of a little under 5.5 kilometers per second. That is the number. Now here is why that number is a problem. When a star swells up into a red supergiant, the way Betelgeuse has, it balloons to hundreds of times its original size. And there is a basic principle of physics that governs what happens to rotation when something expands. It is the same principle that makes a spinning figure skater slow down when she stretches her arms out wide. As a star's outer layers puff outward to enormous size, its rotation should slow dramatically, spreading that spin over a vastly larger body until the surface is barely turning at all. The models are clear about this. A red supergiant like Betelgeuse should be rotating at something less than about 1/10 of a kilometer per second at its surface. Betelgeuse is turning at nearly 5.5. That is not a small discrepancy. The star appears to be spinning something like 50 times faster than a star of its kind has any right to. It is as if the figure skater threw her arms wide and instead of slowing down spun faster. So astronomers were left with a genuine puzzle, and the leading explanation for it is itself unsettling. The idea is that Betelgeuse may have gotten its spin from a collision. Specifically, that at some point in its past Betelgeuse swallowed another star. If the giant merged with a companion star long ago, the orbital motion of that swallowed star, its momentum, could have been dumped into Betelgeuse, spinning it up like a hand giving a top a fresh twist. In this picture, the star we see is not a simple single star that lived a simple life. It is the product of a violent merger, a cannibal that grew fast and strange by consuming a neighbour, and the impossible spin is the leftover fingerprint of that ancient act. Notice something a little eerie about that idea in light of what we just learned. Betelgeuse has a companion now, Siwaha, orbiting so close that it ploughs through the giant's atmosphere and is expected eventually to spiral inward and merge. If the merger idea is right, then Betelgeuse may have eaten a star before, and it may be in the slow process of setting up to do it again. It helps to picture what a stellar merger actually involves, because it is one of the more dramatic things that can happen to a star. Imagine two stars born together, bound in orbit around each other, circling for millions of years. If their orbit slowly tightens through friction or gravitational interactions, the two stars can eventually spiral close enough to touch, and then to merge, the smaller one plunging into the larger and being absorbed, When that happens, all of the orbital motion the two stars carried, all of that spinning momentum does not simply vanish. It has to go somewhere, and much of it gets transferred into the surviving combined star, spinning it up like a skater who has caught hold of a moving partner and been whipped into a faster turn. A star that swallows a companion can emerge from the event rotating far faster than it had any right to, carrying the stolen momentum of its lost partner as a permanent telltale spin. This is why the impossible rotation of Betelgeuse points so many astronomers toward a merger in its past. A single star, evolving quietly on its own, should have spun down to a crawl as it swelled into a supergiant. A star that ate a companion could still be spinning fast because the meal gave it a fresh push. So the strange speed we measure, if it is real, may be a kind of fossil, a memory of violence written into the star's motion, evidence that the Betelgeuse we see is not one star that lived one life, but the fused product of two. And with Siwaha now circling in, slowly losing its orbit to the drag of the giant's atmosphere and expected one day to be swallowed, we may be looking at a star caught in the middle of doing again exactly what it may have done before. If so, Betelgeuse is not just a dying star. It is a serial consumer of its own neighbours, and its impossible spin is the signature of an appetite. But even that unsettling explanation is not safe, because there is a competing idea that pulls the ground out from under the whole question. In 2024, a group of astronomers ran detailed simulations of what the surface of a red supergiant actually looks like, and how it would appear through the same radio telescopes we use to measure the spin, and they raised a troubling possibility. Remember that the surface of Betelgeuse is not smooth. It boils with a few enormous convection cells, continent-sized masses of plasma rising and sinking, each one moving at high speed. Gas rising on one side and sinking on the other could produce almost exactly the same blue and red shift signature that we interpret as rotation. In other words, the star's furious boiling might be masquerading as spin. We might be reading the churn of its surface and calling it rotation. If that is right, then we may not actually know how fast Betelgeuse is turning, or whether the impossible spin is real at all. We might have measured the star's storms and mistaken them for the star's turning. Notice how sharply this contrasts with how well we know our own sun. We can watch sunspots march across the sun's face and time its rotation to within a fraction of a day. We can map its surface in fine detail, track its magnetic cycles, and predict its behavior with real confidence, because the sun presents a steady, fine-grained, well-behaved surface that our instruments were practically designed to read. Betelgeuse denies us all of that. It is not that our tools are weak. The very same techniques that pin the sun down with ease run aground on Betelgeuse, because the star itself refuses to hold still. A face covered in a few enormous shifting cells does not offer the steady reference points that a rotation measurement needs. So a basic property that we nail down almost trivially for the nearest star, how fast it spins, becomes, for the next star out, a genuine open argument between careful scientists. And this is the quiet lesson hiding inside the rotation puzzle. It would be easy to assume that a star as bright and close and famous as Betelgeuse must be, by now, thoroughly understood, its every property measured and filed away. The spin question shows how wrong that assumption is. We are not merely uncertain about some exotic, hard-to-reach quantity here. We are uncertain about whether one of the most conspicuous stars in the sky is spinning quickly, spinning slowly, or fooling us into seeing a spin that is not there. Each answer we reach for, the impossible speed, the ancient merger, the boiling that masquerades as rotation, only widens the gap between how familiar the star feels and how little we actually know. And every step deeper into the question leaves us standing on less solid ground than we thought we had when we started. Step back and feel where we are now. We started tonight with a familiar orange star on a familiar shoulder, a settled and understood thing. And in just a few steps we have found that it can hurl pieces of itself into space, that it hid an entire companion star from us for a century, and now that it may be spinning at an impossible speed, or may not be spinning the way we think at all, and that either way the explanation reaches back to a possible act of stellar cannibalism in its past. Every answer opened two more questions, and we are not done pulling the ground away, because it turns out that even the most basic fact about Betelgeuse, the one number you would think we could nail down, how far away it even is not a fact we actually have. If I asked you how far away Betelgeuse is, you might expect a clean answer. Astronomers are very good at measuring distances to stars, The standard method is beautifully simple in principle. As the Earth travels around the Sun, our viewpoint shifts from one side of our orbit to the other, and nearby stars appear to wobble very slightly against the background of more distant stars, in the same way your thumb held at arm's length appears to jump back and forth when you look at it with one eye and then the other. The size of that tiny wobble tells you the distance. This technique, called parallax, is the foundation of the entire cosmic distance ladder, and for most stars it works wonderfully. But for Betelgeuse, it stumbles, and it stumbles for a reason that is pure Betelgeuse. The problem is that Betelgeuse is not a clean point of light. It is a bloated, boiling, shape-shifting monster whose surface heaves with those enormous convection cells, and whose apparent edge is fuzzy and constantly changing. When you're trying to measure a wobble smaller than almost anything else in astronomy, it helps enormously if the thing you are measuring is a steady, sharp point. Betelgeuse is the opposite. Its surface churns and shifts from month to month, and that churning can slosh the star's apparent position around by an amount comparable to the very parallax wobble you're trying to detect. The star's own restlessness blurs the measurement. This is not a matter of simply building a better instrument either. We have, in orbit right now, an astronomy satellite whose entire purpose is to measure the positions and distances of stars with a precision no ground telescope can match, and it has mapped well over 1 billion of them, pinning down their distances with extraordinary accuracy. For ordinary, well-behaved, point-like stars, it has revolutionized how well we know the map of our galaxy. But Betelgeuse defeats even this. The satellite's method depends on tracking the precise position of a star over months and years and detecting the tiny wobble caused by the Earth's motion around the Sun. That method assumes the star is a stable, sharp point whose true center stays put. Betelgeuse is neither stable nor sharp. Its brightness center wanders as its giant convection cells rise and burst, and that wandering can be as large as, or larger than, the very wobble the satellite is trying to detect. The star is so bright that it actually overwhelms the detectors designed for fainter, better-behaved targets, and so restless that its apparent position shivers from year to year, for reasons that have nothing to do with distance. So we face a strange irony. Our single most powerful tool for measuring stellar distances, a machine that has precisely placed more than 1 billion stars, cannot cleanly measure the distance to one of the brightest and nearest stars in the sky, because that star is too big, too close, too bright, and too turbulent for the technique to work. The very qualities that make Betelgeuse fascinating, its enormous swollen size and its violent boiling surface, are the same qualities that keep us from pinning it down. It is a reminder that being nearby and being well understood are not the same thing. Sometimes the closest objects are the hardest ones to measure, precisely because they are large enough and strange enough to break the tools we built for everything else. So the distance to Betelgeuse comes with an uncomfortably large uncertainty, and different studies over the years have landed on noticeably different answers. For a long time, the textbook figure was somewhere around 640 to 650 light-years. That was the number most people quoted. But the honest published range is much wider than that, running from around 500 light-years on the near side to more than 700 on the far side. And recently, a careful reanalysis pushed the number in a direction that makes the whole thing feel even less settled. That newer work suggests Betelgeuse may be considerably closer than the textbook value, perhaps only around 550 light-years away, roughly a quarter closer than the number we had been using. And if it is closer, then it is also smaller than we thought, because a light that looks a certain brightness from closer up does not need to be as large or as luminous to produce that appearance. Now, you might think a 25% adjustment in distance is a technicality, the kind of thing only a specialist would care about. It is not. The distance to a star is the master key that unlocks almost every other property. If you do not know how far away a star is, you do not truly know how bright it actually is, because a nearer dim star and a farther bright star can look identical from here. And if you do not know its true brightness, you have a harder time knowing its true size and its mass, and crucially where it sits in its life story, how far along the road to death it has travelled. A 25% error in distance ripples outward into every other number we quote about Betelgeuse, softening all of them into ranges. When you read that Betelgeuse is a certain size or a certain brightness or a certain age, you are really reading a number that rests on a distance we are still arguing about. And this is the quiet vertigo of the whole subject. We are not talking about some faint smudge at the edge of the observable universe, some objects so remote that of course our numbers are rough. We're talking about one of the brightest, closest, most studied stars in the entire sky, a star you can find with your naked eye on any winter night, a star human beings have been cataloguing for thousands of years. And we cannot confidently tell you how far away it is. We cannot confidently tell you how big it is. The range of possible sizes people have published runs from a few hundred times the width of our Sun up past 1,000 times, which in the largest estimates would mean that if you set Betelgeuse where our Sun sits, its surface would swallow the inner planets and reach out past the orbit of Mars into the belt of asteroids, so wide that light itself would take hours simply to cross from one side of the star to the other. Or it might be meaningfully smaller than that. We are still working it out. So here we stand, most of the way through our tour of what we have learned, and look at the shape of it. Every single thing we have examined has grown less certain the closer we looked. The dimming, the companion, the spin, and now the distance and the size, the most basic facts of all. It would be fair at this point to feel a little lost, to feel that the star is slipping out of our grasp the harder we grip it. That feeling is exactly right, and it is worth pausing on, because it is the whole point. So let us stop for a moment and gather the pieces together before we go on, because when you stack them up in one place, the pattern they form is the real story of Betelgeuse. Let me pull the threads into one place, because we have covered a lot of ground, and the pattern only becomes clear when you see it all at once. Set the individual mysteries side by side and look at them together. We began with the Great Dimming, a star that faded so far and so fast that it changed the shape of a constellation and made the world wonder if it was dying. We asked what caused it, and we got our answer. The star had ejected a piece of itself, an amount of material almost beyond comparison, and hidden behind the resulting dust. That answer was real, and it was satisfying, and it also revealed a star far more violent and unpredictable than we had assumed. One question answered, a larger one opened. Then we turned to the slow rhythm, the 6-year pulse that a century of astronomers had measured and none could explain. We asked what caused it, and again we got our answer. A companion star, Siwaha, hidden in the glare for 100 years, circling so close it ploughs through the giant's own atmosphere and drags a wake of gas behind it. That answer was real, confirmed by the star's own telltale trail, and it revealed that we had been miscounting the very object we watch most closely, that a whole star had been sitting there unseen the entire time. One question answered, a larger one opened. Then the spin. We measured how fast Betelgeuse turns and found a speed that should be impossible for a star its size, 50 times faster than the rules allow. We reached for an explanation and found one, that the star may have swallowed a companion in its past and stolen its motion, a possible cannibal wearing the evidence on its sleeve, and then even that was thrown into doubt, because the impossible spin might not be spin at all, but the boiling of the surface fooling our instruments. One question answered, 2 more opened, and then the distance, and with it the size. The most basic facts you could ask about a star, and we cannot pin them down, because the star is so restless that it blurs its own measurement, and the newest work moved it a full quarter closer than the textbooks say, softening every other number into a range. Do you see the shape now? This is the thing I asked you to watch for at the very beginning. Every answer opened 2 more questions. That phrase has followed us through the whole tour, and by now it has stopped being a clever line and started being a genuine description of how this star behaves under study. There is a comforting story we tell ourselves about science, that it is a steady march from ignorance toward understanding, that the more we look at a thing, the more it comes into focus, the smaller its mysteries become. Betelgeuse runs that story backward. The more instruments we turn on it, the more time we spend with it, the more papers we write about it, the less settled it becomes. It is not that we are learning nothing. We are learning a great deal. It is that each thing we learn reveals how much more there was that we did not know we did not know. And I want to be precise about why this particular ignorance is so unsettling, because it is a different kind from the sort we're used to hearing about. We are accustomed to being told that the far reaches of the universe are mysterious, that the earliest moments of the Big Bang, the interior of a black hole, the nature of dark matter, are beyond our full understanding. That kind of mystery feels acceptable, even natural, because those things are unimaginably remote, or unimaginably extreme. Of course, we do not fully understand the edge of the observable universe. It is billions of light years away. But Betelgeuse is not remote. It is one of the nearest bright stars to us, a naked-eye object, a fixture of the winter sky, a thing our ancestors named thousands of years ago. It is, in cosmic terms, practically in our backyard, and we cannot say how far away it is, or how big it is, or how fast it spins, or how close it is to death, or even, at this moment, whether it is still alive. That is what turns the ordinary humility of science into something closer to vertigo. It is one thing to admit we do not understand the exotic and the distant. It is another to admit that we cannot pin down the basic facts of a bright star we can see with our own eyes any clear night. It suggests that the gap between looking at something and truly knowing it is far wider than we usually let ourselves believe. We have been looking at Betelgeuse for the whole of human history, and it turns out we have been looking at a portrait we cannot quite read, of an object stranger than we assumed, doing things our models did not predict, keeping its most important secret, the state of its hidden core, permanently out of reach. If that is true of the star on the hunter's shoulder, the one we know best, then it is a quiet warning about how much of the rest of the sky we are also only guessing at. And here is why that matters, why it is not just an interesting quirk of one star. Because up to this point, every mystery we have looked at has been about the outside of Betelgeuse, the surface that ejected the dust, the atmosphere the companion ploughs through, the churning face that fools our measurements of spin and distance. All of it is the outer star, the part we can see. But the real clock, the one that will decide when this star dies, is not on the outside at all. It is buried at the very centre, in a core that no telescope will ever see, running a countdown we cannot read. And to understand why that countdown is so frightening, and why we genuinely cannot tell you whether it has years or 100,000 years left to run, we have to leave the surface behind and go all the way down, into the heart of the star, and climb the ladder that leads, one rung at a time, to Orion. To understand the clock inside Betelgeuse, you have to understand what a star actually is, at the most basic level. A star is a balance. It is a constant, roaring struggle between two opposing forces, and that struggle is the whole of a star's life. On one side is gravity, pulling every part of the star inward, trying to crush the entire enormous mass down toward its own centre. Gravity never rests and never weakens. It is always pulling, always trying to collapse the star. On the other side is the outward push of energy generated in the core, the pressure of heat and radiation streaming outward from the fires at the centre. As long as those fires burn, they push outward hard enough to hold gravity off, and the star stays inflated, stable, shining. A star is a thing that is holding itself up against its own weight by burning, and the moment it can no longer burn, it falls. The fire in the core is nuclear fusion. In the heart of a star, under crushing pressure and enormous heat, atomic nuclei are forced together and fuse into heavier ones, and that fusing releases energy. For most of a star's life, the fuel is hydrogen, the lightest and simplest element, and the star fuses hydrogen into helium. Our Sun is doing this right now, and it has been doing it for over 4.5 billion years, and it will keep doing it for billions more. Hydrogen fusion is slow and steady and long-lasting, and it is what makes a stable, ordinary star. But Betelgeuse is not an ordinary star, and it is not slow, and it is not long-lasting. Betelgeuse is enormously more massive than the Sun, somewhere between roughly 16 and 19 times the Sun's mass, and mass changes everything. The more massive a star is, the harder gravity crushes its core, and the hotter and denser that core becomes, and the faster it burns through its fuel. This is one of the cruel bargains of the universe. A massive star is brighter and more powerful, but it pays for that brilliance by devouring its fuel at a furious rate and living a spectacularly short life. Betelgeuse is only about 8 to 10 million years old. Our Sun, by comparison, is 4.5 billion years old and barely middle-aged. Betelgeuse, despite being an infant by the Sun's standards, is already dying, already near the end, because it has been burning so hard and so fast that it has nearly run through everything it has. It is a child that is also an old man, and that contradiction is written into its mass. Here is what happens as a massive star nears its end, and it is one of the strangest and most relentless processes in all of nature. When the star exhausts the hydrogen in its core, the fire does not simply go out. The core, no longer pushed outward as strongly, contracts under gravity, and contracting makes it hotter, and at that higher temperature a new fuel ignites. The helium that was the ash of hydrogen burning now becomes fuel itself, and the star begins fusing helium into carbon and oxygen. When the helium runs out, the core contracts again, grows hotter again, and lights a new fire, fusing carbon into heavier elements still. It is a ladder. Each time one fuel is exhausted, the core shrinks and heats and ignites the ash of the previous stage, climbing rung by rung to heavier and heavier elements. Carbon burns to neon, neon burns to oxygen, oxygen burns to silicon, and each rung of that ladder burns faster than the one before it, far faster. Let me put you inside the star, because this is where it stops being a diagram and starts being a countdown. Imagine you could descend into Betelgeuse, sinking down through its layers toward the center. Near the surface, you pass through the cool, thin outer atmosphere, the churning orange gas, the region where the companion ploughs its wake. You keep sinking. Below that, the hydrogen is still fusing in a shell, a burning layer wrapped around the deeper core, and it has been doing so for ages. You sink deeper, and the temperature climbs, and you pass into a shell where helium is fusing into carbon, faster and hotter. Deeper still, and you reach a layer where carbon is fusing, and here the timescale has collapsed from millions of years to mere centuries. Deeper, into the neon-burning shell, and now the clock runs in single years. Into the oxygen shell, and the star is consuming its fuel in months. And then the silicon, the last rung before the end, and here the fire burns so ferociously that the star fuses through its entire supply in a matter of days. You're standing near the center of a star that has spent millions of years getting here, and the final stages flash past in days. The layers nested inside one another like the rings of an onion, each inner ring burning faster than the last, the whole structure racing toward a center that is filling moment by moment with a single fatal element. Let me stay with iron a moment longer, because the reason it ends the star is one of the most elegant and merciless facts in all of physics, and it is worth understanding properly. Every atomic nucleus can be thought of as sitting somewhere on a slope of stability. Light nuclei like hydrogen and helium sit high on one side of a valley, and when you fuse them together, they slide downhill toward greater stability, and the energy they lose on the way down is released as the light and heat of the star. That downhill slide is what powers every star in the sky. But the valley has a bottom, and iron sits precisely at that bottom. It is the most tightly bound, most stable arrangement of nuclear matter there is. You cannot slide downhill from iron, because there is no downhill left. Fusing iron into anything heavier means climbing back up the far slope, and climbing costs energy rather than releasing it. So when the core of Betelgeuse turns to iron, the star has, in the most literal sense, hit the bottom of the well. There is no next fuel, no next rung, no way to keep the fire going, and the situation is worse than simply running out, because the silicon burning in the shell just above the core keeps producing fresh iron and dumping it down onto the growing iron center. So the core does not just stall, it grows heavier by the second while producing no supporting energy at all. It is like pouring more and more weight onto a floor while switching off the very thing that was holding the floor up. The star has spent millions of years climbing this ladder, and the ladder has led it to a trap of its own making, and the cruelest part is the speed. Hydrogen burning lasted millions of years, helium hundreds of thousands, carbon centuries, neon a year or so, oxygen months, silicon days. The final iron-building stage is the shortest of all. A star can spend more than 99% of its entire life on the first rung, and race through the last few rungs in the span of a single human lifetime or less. Somewhere inside Betelgeuse, that acceleration is either still to come or already underway, and we have no way to see which. That element is iron. Iron is the end of the ladder, and it is the end for a reason written into the deepest laws of physics. All the way up the ladder from hydrogen to silicon, fusing lighter elements into heavier ones released energy. That released energy is the outward push, the fire that holds gravity off. But iron is different. Iron is the most tightly bound nucleus there is, sitting at the very bottom of a kind of energy valley. To fuse iron into anything heavier does not release energy. It costs energy. It takes energy in rather than giving energy out. So when the core of the star becomes iron, the star reaches a wall it cannot climb. The fire that has held the star up for millions of years, through every rung of the ladder, suddenly has nowhere left to go. The iron core sits there, growing heavier as the silicon shell above it keeps dumping fresh iron down onto it, and it gives nothing back. For the first time in the star's entire life, the outward push falters, and gravity, which has been waiting patiently the whole time, which never rested and never weakened, is finally about to win. And here is the terrible essential fact, the one that makes the whole clock unreadable. Everything I have just described is happening in the core, at the very center of the star, buried under all those layers of burning shells and churning atmosphere. We cannot see any of it. Not a bit. Every single thing we observe about Betelgeuse, its brightness, its color, its pulsing, its dimming, its wake, comes from the outer layers, from the atmosphere and the surface. The core is sealed away beneath hundreds of millions of kilometers of star, and no telescope that will ever be built can see through that to read what rung of the ladder the core is on right now. The countdown is running, we just cannot see the clock, and when the iron core finally reaches its breaking point, everything that happens next happens in less than 1 second. When the iron core of Betelgeuse crosses its limit, the end does not come slowly. It comes faster than almost anything else in the universe. There is a specific threshold, a maximum mass that a core held up by a certain kind of quantum pressure can bear, equal to about 1 4/10 times the mass of our entire sun. As the silicon shell keeps raining iron down onto the core creeps toward that limit, and the instant it crosses it, the support gives way completely. The core, an object more massive than the sun but by then squeezed down to roughly the size of the Earth, can no longer hold itself up, and it collapses. Not over years or days or even minutes, it collapses in a fraction of a single second. Try to hold the scale of this in your mind, because it is one of the most extreme events physics allows. An object heavier than the sun, the size of a planet, falls inward on itself so fast that its outer edge rushes toward the center at a substantial fraction of the speed of light. In less time than it takes you to blink, that Earth-sized core is crushed down until it is only a few kilometers across, the size of a city. Matter is squeezed to a density so extreme that the empty space inside atoms is wrung out of them entirely. Protons and electrons crush together into neutrons until the whole collapsing core becomes something like a single, monstrous atomic nucleus the size of a mountain range. A teaspoon of that material would weigh as much as a mountain. It is worth dwelling on what that crushed remnant actually is, because it is one of the most extreme objects the universe knows how to make. A neutron star packs more than the entire mass of our sun into a ball only a handful of kilometers across, roughly the size of a city. The density is beyond ordinary comprehension. The matter is squeezed so tightly that atoms as we know them cannot exist. Their internal empty space wrung completely out, leaving something closer to a single continuous mass of neutrons packed shoulder to shoulder. These objects can spin astonishingly fast, some of them turning hundreds of times every second, sweeping beams of radiation across space like the most precise lighthouses in existence, so regular that they rival atomic clocks. The neutron star that Betelgeuse will leave behind would be exactly this kind of object, a tiny, dense, fiercely spinning ember, all that remains of a heart that once held a star the size of a planet's orbit up against its own gravity. And the energy of the moment that creates it is genuinely difficult to state in a way the mind can hold. When the core collapses, the gravitational energy released is so enormous that, as we said, it briefly exceeds everything the sun will radiate across its entire multi-billion-year lifetime. The overwhelming majority of that energy pours out as neutrinos in a matter of seconds, a flood so intense that if you were anywhere near the star, the neutrinos alone, those particles that normally slip through worlds without touching anything, would be lethal, which almost never happens anywhere in nature. Only a small fraction of the total energy goes into the visible explosion and the shock wave that shreds the star, and yet that small fraction is still enough to outshine a galaxy for weeks. When you look at the numbers, the death of a massive star is not merely large. It sits near the very top of the scale of violent events that the universe permits, and Betelgeuse has that ending waiting inside it. That crushed remnant, a neutron star or, if enough matter falls back in, a black hole, is what the collapse leaves behind at the very center. And then the collapse rebounds. When the infalling core slams into that newly formed, incompressibly dense center, it hits a wall that will not give, and it bounces. A shockwave is born at the center and begins to tear back outward through the star. At the same instant, the crushing together of all that matter releases an almost incomprehensible flood of ghostly particles called neutrinos, and this is where the real energy of the event lives. The number is difficult to write in a way that means anything, so let me try it this way. In the moment of collapse, Betelgeuse will release more energy than our Sun will radiate over its entire 10 billion year lifetime. All of it. Everything the Sun will ever pour out across its whole existence, unleashed by Betelgeuse in a matter of seconds. The overwhelming majority of that energy escapes as neutrinos, streaming out through the star as if it were not even there, and what is left, the shockwave and the radiation, tears the rest of the star apart from the inside. This is the supernova, the outer layers of Betelgeuse, all those shells of hydrogen and helium and carbon, all the churning atmosphere, everything except the crushed remnant at the centre, is blasted outward into space at thousands of kilometres per second. For a few weeks, the explosion shines with the light of billions of suns, bright enough to be seen across the galaxy and beyond, a single star briefly outshining the combined glow of every other star in a galaxy. The material thrown outward carries with it all the elements the star forged over its lifetime, the carbon and oxygen and the heavier elements, seeding the surrounding space with the raw material of future stars and planets, and, eventually, of living things. This is not only destruction, it is the way the universe manufactures and distributes the very atoms that make worlds and make us. The iron in your blood, the calcium in your bones, the oxygen you're breathing right now, all of it was forged and scattered by dying stars doing exactly what Betelgeuse is about to do. But I want to bring you back from the poetry of it to the hard, specific fact that this whole video has been circling, because it is the thing that makes Betelgeuse frightening in the particular way that it is. Everything I have just described, the collapse, the rebound, the neutrino flood, the explosion, is triggered by the state of the iron core, and the iron core is invisible to us. We have just walked through the death of the star in vivid detail. We understand the physics of it well enough to describe it second by second, and yet we cannot tell you when it will happen, because the one piece of information that would tell us the exact condition of that hidden core right now is sealed away where no instrument can reach. We can describe the ending perfectly, we simply cannot read the clock that starts it, and so we are left in a genuinely strange position with respect to Betelgeuse. We know, with real confidence, how the star will die. We know it will collapse and rebound and explode as a supernova, leaving behind a neutron star or a black hole inside an expanding cloud of enriched gas. We know the sequence, the physics, the energy, the outcome. The only thing we do not know is the single thing everyone actually wants to know, which is when. And it turns out that when you press on that question honestly, the answer is not a date, and it is not even a good estimate. The answer is a shrug that spans 100,000 years, and inside that shrug hides a small, disputed, and deeply uncomfortable possibility that the moment might be much, much closer than anyone would like. So let us ask the question directly, the one that has been hovering over this star since the moment it first dimmed. When will Betelgeuse explode? You would think, after everything we have measured about this star, after imaging its companion and tracing its wake and clocking its impossible spin, that we could at least give a decent answer to the most basic question of all. We cannot. And the reason we cannot is the thing we established a moment ago. The trigger is in the core, and the core is invisible, and everything we can actually observe is the outer star layers and layers removed from the iron that decides the moment. The standard answer that astronomers give, when pressed, is that Betelgeuse will likely go supernova sometime in the next 100,000 years. Now sit with how strange an answer that is. 100,000 years. That is not a prediction. That is an admission of ignorance dressed up as a number. It means the explosion could happen tonight, while you are listening to this, or it could happen roughly 4,000 human generations from now, long after everyone alive today and everyone they will ever know has turned to dust and been forgotten. And both of those possibilities are entirely consistent with everything we can measure. On the scale of a star that has already lived for millions of years, 100,000 years is the blink of an eye, a rounding error at the very end of its life. But on the scale of a human life, it is an ocean of time so wide that saying the event lies somewhere within it tells you almost nothing at all. And it gets more unsettling than a simple wide range because not everyone agrees the range is that comfortable. In 2023, a group of astronomers took a close look at the way Betelgeuse pulses, those rhythms of brightening and dimming we talked about earlier, and they tried to use the pulsations to read the star's internal state. the way a doctor might read something about your heart from the rhythm of your pulse. Their conclusion was alarming. They argued that the specific way Betelgeuse pulses is best explained if the star is already burning carbon in its core, which is a very late stage on that ladder to Orion, much closer to the end than most people had assumed. If they were right, then the comfortable 100,000-year cushion collapses, and Betelgeuse might be only centuries or even less from its death. Not 100,000 years. Centuries. Now, I want to be careful and honest here, the way this channel always tries to be, because that alarming study did not go unchallenged. Very quickly, other astronomers pushed back, arguing that the pulsation reading was not reliable, that the interpretation of the star being in late carbon burning did not hold up, and that the evidence did not support such an imminent timeline. The dispute is not settled, and it may not be settleable, precisely because both sides are trying to infer the state of a core that neither of them can see. That is the maddening heart of it. The argument over whether Betelgeuse has centuries or 100,000 years left cannot be resolved by simply looking harder, because the answer is locked in the one place looking cannot reach. We are reading tea leaves in the star's outer pulses and trying to guess at the iron in its heart. It is worth understanding why the pulsations tempt us at all, and why they cannot quite deliver. When a star pulses, swelling and shrinking on a regular rhythm, the length of that rhythm depends on the structure of the star, on how its mass is arranged from centre to surface. In principle, then, the pulsations carry a faint fingerprint of the star's interior, in the same way the ringing tone of a bell carries information about the bell's shape and thickness. This is a real and powerful technique in astronomy, and for many stars it works beautifully, letting astronomers sound out the hidden interior from the outside. The trouble with Betelgeuse is that a bloated, boiling red supergiant is about the hardest possible case. Its outer layers are turbulent and poorly understood, its structure is uncertain, and its various overlapping rhythms, the 400-day pulse, the 6-year companion cycle, and others, tangle together in ways that are difficult to separate cleanly. Reading the interior from the surface here is less like hearing a clear bell tone, and more like trying to guess the shape of a room from the muffled noise coming through a thick wall. That is why the 2023 claim of late carbon burning could be made at all, and also why it could be so quickly disputed. Both sides were listening to the same muffled sound and reaching different conclusions about the room behind the wall. And there is no easy tiebreaker, because the only thing that would settle it, a direct look at the core, is exactly what nature forbids. So we are left with a genuine and possibly permanent uncertainty, not a temporary gap that better instruments will soon close, but a wall built into the physics of the situation. Betelgeuse could be a late-stage star with only centuries left, or it could have tens of thousands of years to go, and honest astronomers will tell you that both remain on the table. It is a rare and humbling thing in modern science to face a question this simple. When will this specific star die? And to have to answer truthfully that we do not know and may not be able to know until it actually happens. This is the emotional centre of the whole story, and I want to let it land fully. We can measure this star's colour and its temperature. We can clock its pulsing to the day. We can detect a companion nobody had ever seen and trace the wake it leaves in the atmosphere. We can measure a rotation that should be impossible. We have poured more attention onto this one star than onto almost any other in the sky. And after all of it, we cannot answer the question a child would ask first, the simplest question there is, when? To stand under Betelgeuse and know that it is going to explode, to know exactly how and exactly what will happen, and to have no idea whether it will be tonight or in 100,000 years, is to hold a countdown whose numbers are hidden from you. The clock is real, it is ticking, and the face of it is turned away from us forever. And notice what that does to the very word imminent. When astronomers say Betelgeuse could go supernova at any moment, they mean it in the honest, literal way. Any moment. There is no reassuring physics that lets us rule out tonight, but there is also no physics that lets us expect tonight. The star exists for us, in a kind of permanent suspension, always potentially about to end and never predictably so. A sword hanging on a thread we cannot see the thickness of. There is something almost philosophical in this suspension, and it is worth sitting with because it is so unusual. For nearly everything else in our lives, uncertainty about timing comes in manageable sizes. We do not know exactly when it will rain, but we can say it looks likely this week. We do not know exactly when a distant comet will return, but we can often predict it to the year. Betelgeuse offers no such comfort. The honest window on its death spans from tonight to 100,000 years from now, and nothing we can currently measure narrows it in a way that would satisfy anyone. It is uncertainty of a scale that human intuition simply is not built to hold. We want the question when to have an answer shaped like a date, or at least like a decent estimate, and instead it has an answer shaped like a shrug that outlasts civilizations. And so, the only honest posture toward Betelgeuse is a kind of patient watching without expectation. Astronomers do not lie awake expecting it tonight, because there is no reason to think tonight is special. But they also cannot rule tonight out, because there is no reason to think it is safe either. The star simply sits there in its permanent maybe, glowing on the shoulder of the hunter, capable of erupting at any moment and equally capable of glowing on, unchanged to our eyes, for longer than our species has so far existed. To watch it honestly is to hold both of those possibilities at once, without collapsing into either the panic of imminence or the false calm of certainty. It is one of the very few things in the sky that keeps us in that exact state of open, unresolved attention, and that, more than any danger, is what makes it so hard to look away from. That is a genuinely uncomfortable thing to hold in the mind, and it is the truest description of our relationship to this star. But before you let that discomfort curdle into fear, I need to turn the whole thing around, because there is one more question we have not yet answered, and it is the one that finally converts all of this dread into something else entirely. What actually happens to us down here on our small blue world on the night that Betelgeuse finally dies? Here is what will happen on the night that Betelgeuse dies, and I want to describe it carefully, because after all the dread we have built up, this is the part that transforms it, and it deserves to be seen clearly. When the core of Betelgeuse collapses and the star tears itself apart, the light of that explosion will begin crossing the space between us, and when it arrives, the sky will change in a way that no living human being has ever witnessed. There has not been a supernova this close, this bright, in the era of recorded history. What is coming, whenever it comes, will be the single most spectacular event our sky has offered in all the time that humans have been looking up. Let me give you the numbers first, and then let me put you underneath it. When Betelgeuse explodes, at its peak, it will shine roughly as bright as the moon. Different estimates put it somewhere between the brightness of a half moon and a full moon. But here is the crucial difference, and it matters enormously for how it will look. The moon's light is spread across a disk, a soft circle in the sky about half a degree wide. Betelgeuse, even in explosion, will be so far away that its light will arrive as a single point, a pinprick of brilliance rather than a spread-out glow, and a point of light carrying nearly the total brightness of the moon, concentrated into something the eye reads as a single dazzling spark, will look more intense, more piercing than the moon ever does. It will be a second source of real light in the sky, a hard, bright point that you cannot look away from. It will be visible in broad daylight. This is not an exaggeration. For weeks, there will be a second point of brilliance hanging in the daytime sky alongside the sun, easily visible, a star bright enough to hold its own against the blue of noon. People will step outside at midday and see two lights up there, the sun and the dying star, and there will be no way to pretend it is ordinary. And at night, the explosion will be bright enough to cast shadows, real shadows, the way a full moon throws faint shadows of trees and buildings across the ground. If you were somewhere truly dark, with the city lights switched off and no clouds overhead, you would be able to read a book by the light of Betelgeuse, by the glow of a star that died 5 centuries ago and hundreds of light years away. It will hold that brilliance for weeks, and then slowly, over months, and finally more than a year, it will fade, dimming and dimming until at last it winks out and is gone. Let me put you there, on that night, because the numbers do not carry the feeling of it. You step outside on an ordinary evening, you're not expecting anything. The sky is the sky you have always known, the same one from your childhood, Orion climbing in the winter dark with his belt and his familiar shoulders, and then you see it. Where the soft orange star used to sit on the hunter's shoulder, there is now a point of light so bright it stops you where you stand. It is not orange anymore. It is a fierce white-blue spark, brighter than any star you have ever seen, brighter than the planets, so bright that when you look away you carry its afterimage. Over the following nights it climbs brighter still, until it is casting your shadow on the ground behind you, a faint, sharp shadow thrown by a single star. During the day it hangs there beside the sun, a second brilliant point that everyone can see, that children will ask about, that no one will be able to ignore. For weeks the world has two lights, and you understand, standing there in the doubled light, that you are watching a star die, that this brilliance is the last thing Betelgeuse will ever do, the final act of an object that hung quietly on that shoulder through every human generation that came before yours, and then, slowly, over the turning of the seasons, it fades. The second sun dims. The shadows it threw grow soft and vanish, and one night you look up, and the shoulder of Orion is simply empty, a gap where a star used to be, and the constellation that looked the same for 40,000 years has been changed forever, in your lifetime, before your eyes. That is the death of Betelgeuse as it will appear to us. Not a catastrophe, a spectacle. The most beautiful and most humbling thing the sky can show, a second sun kindled and then extinguished, a permanent edit to a picture humans have been drawing since the Ice Ages, and the fading itself will be its own slow drama, drawn out across a length of time that will let whole seasons pass beneath it. A supernova does not simply flash and vanish. It flares to its blinding peak over days or weeks, holds there, and then begins a long, gradual decline that unfolds over many months, the light powered in its later stages by the radioactive decay of the new elements forged in the blast. So this will not be a single spectacular night that people happen to catch or miss. It will be a months-long presence in the sky, a second light that everyone on Earth will have time to notice, to grow used to point out to their children, to watch slowly dim from that first fierce brilliance down through fainter and fainter stages, week after week, until at last it drops below the threshold of the naked eye, and the shoulder of Orion goes dark for good. People will remember where they were when it first appeared. They will remember the strange doubled light of those weeks, the shadows on the ground at night, the point of brilliance beside the noonday sun. It will become a shared memory for an entire generation of humanity. The season the sky had two suns, and then the quieter season when one of them faded away and a familiar constellation was left changed forever. No one who lives through it will ever look at Orion the same way again, because the shoulder they grew up with will simply not be there anymore. And I have called it beautiful and safe, and I need to make good on that word safe. Because the whole time I have been describing this, some part of you may have been waiting for the catch. A star exploding with the energy of billions of suns, close enough to cast shadows on the Earth. Surely, you might think, something that violent, that near, must be dangerous. Surely a second sun in the sky comes with a cost. It is the most natural fear in the world, and it is the last thing standing between us and understanding this star clearly. So let us take it head on and lay it to rest, because the truth is the most reassuring part of the entire story. The fear that an exploding Betelgeuse could harm the Earth is old, and it is understandable, and it is wrong, and I want to explain exactly why, because the reasons are solid and the reassurance is real. A supernova is genuinely one of the most violent events in the universe. If the Earth were too close to one, the consequences would be severe. The blast floods space with high-energy radiation and with fast-moving particles called cosmic rays, and a sufficiently near supernova could damage the layer of ozone that wraps our planet and shields the surface from the sun's harmful ultraviolet light. Strip away enough of that ozone and you expose the living things below to radiation they are not built to survive, and you could, in principle, trigger a genuine catastrophe. This is not fantasy. Astronomers take the threat of nearby supernovae seriously, and there is evidence written in the Earth's own layers that distant explosions have brushed our planet in the deep past. So the real question is simply one of distance. How close does a supernova have to be to hurt us? And the answer is the thing that makes Betelgeuse safe. For a supernova to seriously damage the Earth's atmosphere and threaten life, it would need to detonate within roughly 30 light-years of us. That is the danger zone, the radius inside which an exploding star becomes a genuine threat. Even the most cautious estimates, the ones that try to account for every indirect way a blast might reach out and touch a distant world, push that boundary out to somewhere around 160 light-years. Beyond that, the explosion is a light show, not a weapon. Its energy spreads out across the widening distance and thins into harmlessness long before it reaches us. Now recall how far away Betelgeuse is. Even by the newest and closest estimate, the one that pulled it a quarter nearer than the textbook said, Betelgeuse sits at something like 550 light-years away, and by the traditional figure it is well over 600. Set that against the danger zone, 30 light-years for real damage, 160 at the very most cautious outer edge, and Betelgeuse is at least 550. It is more than 3 times farther away than even the most conservative danger line, and something like 18 times beyond the zone of serious harm. When Betelgeuse explodes, the radiation and the particles that reach us will be diluted by all those hundreds of light-years of distance into something utterly harmless. The neutrino flood will wash through the Earth and through your body without you feeling a thing, detectable only by the most sensitive instruments we have built, and priceless to science. But it will not hurt you. It will not hurt anyone. In fact, that harmless neutrino flood would be one of the greatest scientific gifts imaginable. A close supernova would let physicists study the death of a massive star and the extreme physics of the collapsing core in a detail that no distant explosion could ever provide, testing our deepest theories about matter, gravity, and the particles that make up the universe. The same event that some people fear as a threat would, in reality, be a windfall for human understanding, a chance to learn things about the fundamental workings of nature that we could gather in no other way. The danger is imaginary. The opportunity would be real. The star is close enough to put on the greatest show the sky has ever staged, and far enough away that the show is all it will ever be. There are a few darker stories that circulate about Betelgeuse, and in the spirit of looking at everything honestly, let me address them, because meeting a fear directly is the best way to dissolve it. Some people worry that the explosion will fry the Earth, that a supernova on our doorstep must mean an extinction. We have just seen why that is not so. The star is far outside the range where it could do any harm at all. The distance does all the work, and the distance is not in doubt in the way that matters here, because even the nearest possible estimate leaves Betelgeuse comfortably, enormously, beyond the reach of danger. Others wonder, uneasily, whether the star has already exploded and the truth is being kept from them, whether somewhere someone knows and is not telling. And here the answer is almost gentle. There is nothing to hide and no one who could hide it. When Betelgeuse's light arrives, it will arrive for everyone at once, all over the Earth, seen by millions of eyes and thousands of telescopes in every country in the same instant. A supernova is the least secret event imaginable. It is a second sun in the daytime sky. There is no authority on Earth that could conceal a light that casts shadows, and no reason anyone would want to. The idea of a covered-up supernova mistakes the most public event in the heavens for something that could be whispered away. And a few imagine that a distant stellar explosion could somehow reach across the light years and shift the Earth's poles, or tip the planet, or disturb us physically in some direct way. There is simply no mechanism for it. A supernova hundreds of light years away sends us light, and eventually a thin drizzle of harmless particles. It does not send a push. It cannot nudge the Earth or turn it or shake it. The planet will feel nothing. The only thing that will reach us is the light, and light, however bright, does not move worlds. If you want proof that a distant supernova is survivable, the Earth itself has kept the receipts. Buried in the deep layers of the ocean floor and even in samples brought back from the Moon, scientists have found traces of a particular form of iron, a rare radioactive variety that is not made in any ordinary process here on Earth. It is forged in supernovae. Its presence in those ancient layers is a physical record that debris from one or more nearby stellar explosions actually drifted through our solar system and settled onto our planet, and the depth of the layers tells us roughly when. The signal points to explosions a few million years ago, from stars estimated to have been a few hundred light-years away, in the same broad range of distance as Betelgeuse. And here is the reassuring conclusion. Those explosions happened. Their debris reached us, and life on Earth carried on. There was no extinction tied cleanly to them, no sterilized planet, just a faint dusting of exotic iron laid down in the rocks, and the slow continuation of everything that was living. The Earth has already lived through supernovae at roughly Betelgeuse's distance more than once, and it is still here, and so are we. That is the deep context that should finally settle the fear. We are not speculating about whether a supernova hundreds of light-years away is survivable. We have the geological evidence that it is, written into our own seafloor. The 30 light-year danger zone and the more cautious 160 light-year outer limit are not comforting guesses. They are boundaries drawn from physics and confirmed, in their own way, by the fact that our planet has been brushed by these events and kept its atmosphere and its oceans and its life intact. Betelgeuse, sitting at 3 or 4 times even the outermost cautious distance, is not a threat of any kind. When it goes, it will be the most magnificent thing our sky has ever done, and it will leave us completely unharmed, exactly as its distant predecessors did. So here is the honest shape of the danger, and it is almost the opposite of what the fear expects. The thing people are frightened of, being physically harmed by the explosion, is the one outcome we can very nearly rule out. Betelgeuse is a spectacle that cannot touch us. And the thing that should genuinely humble us, the thing that is actually unsettling about this star, is not the explosion at all. It is everything we have spent this whole time uncovering. It is how little we truly understand about it. The danger was never that Betelgeuse would hurt us. The unease was always about knowledge, about standing under a familiar sky and slowly realizing how much of it we are only guessing at. And there is one final piece of that unease, one last turn of the screw, and it is the strangest thing of all because it means that everything we have been discussing tonight, the countdown, the timing, the question of when, may already be settled, and we simply do not know it yet. There is a peculiar and little-known fact about how a supernova announces itself, and it turns out that we might get a warning before Betelgeuse's death ever becomes visible in the sky. To understand it, we have to go back to those neutrinos, the ghostly particles that carry away almost all of the energy when the core collapses. Neutrinos are the strangest of ordinary particles. They barely interact with matter at all. They stream through solid rock, through planets, through you, as if none of it were there. Trillions of neutrinos from our own sun are passing through your body every second right now, and you feel nothing, and they leave no mark. That ghostliness makes them nearly impossible to catch, but it also gives them a remarkable property. When a star's core collapses, the neutrinos escape instantly, pouring straight out of the center and away into space at almost the speed of the light. The light of the explosion, by contrast, does not escape instantly. The visible flash is born deep inside the star when the shockwave reaches the surface, and even after that the light has to fight its way out through all the debris and gas of the exploding star. So the neutrinos get a head start. They leave the moment the core dies, while the light is still trapped inside, working its way to the surface. By the time the first light of the supernova breaks free and begins its journey to us, the neutrinos are already hours ahead, racing across the light years in front of the glow. And so, when Betelgeuse finally goes, the very first thing to reach the Earth will not be the light at all. It will be a silent, invisible pulse of neutrinos, arriving hours before the sky lights up. We know this is true because we have seen it happen once before, in a manner of speaking. In 1987, a star exploded in a small companion galaxy near our own, and detectors here on Earth caught a brief burst of neutrinos from that collapse. It was the first time humanity ever detected neutrinos from a dying star, a handful of ghostly particles registered in underground tanks, and the light of that supernova arrived in our sky a few hours after the neutrinos did, exactly as the physics predicted. That event, hundreds of times farther away than Betelgeuse, gave us only a whisper of neutrinos. Betelgeuse, so much closer, would give us a roar, a flood of neutrinos so large that our detectors would light up unmistakably. Because of this, astronomers have built a kind of alarm system, a network of neutrino detectors around the world that watch, constantly, for exactly this signal. The idea is that if a nearby star's core collapses, the detectors would catch the neutrino burst and sound an automatic alert, telling astronomers everywhere to point their telescopes at the sky and get ready, because in the next few hours a star is about to become visibly, spectacularly bright. It is an early warning system for the death of a star. These detectors are strange and wonderful machines in their own right. Because neutrinos slip so easily through ordinary matter, catching even a few of them requires enormous volumes of material buried deep underground, shielded from the ordinary rain of cosmic particles that would otherwise drown out the signal. Some are gigantic tanks of ultra-pure water, others use other dense materials, all of them watched by sensitive light detectors waiting for the extraordinarily rare flash that marks a neutrino interacting with a single atom inside. On any ordinary day they catch a trickle, a stray particle here and there from the sun or from the atmosphere, but when a nearby star's core collapses, that trickle would become a sudden burst, a spike of neutrino detections all arriving within seconds of one another, unmistakable against the quiet background. The detectors scattered around the world are linked together in a coordinated network precisely so that if several of them see such a burst at the same instant, an automatic alert can go out immediately, before any human even looks at the data. The purpose of that alert is to buy astronomers those few precious hours between the neutrinos and the light. If the warning fires, telescopes everywhere could swing toward the expected part of the sky and begin recording before the visible explosion even starts, capturing the very first moments of the light as it breaks free, moments that have never been observed in detail for any nearby supernova. It would be the astronomical event of not just a lifetime, but of the entire history of the science, and the neutrino network exists to make sure that when it comes, we are watching from the first instant. And if the star that triggers it turns out to be Betelgeuse, then that alert would carry a particular chill, because it would be the confirmation, arriving hours early and in perfect silence, that the familiar orange star on the hunter's shoulder was already gone. And if Betelgeuse is the one that goes, that alarm would give us a few precious hours of forewarning, a window in which we would know, with certainty, that Betelgeuse had already died, that its core had already collapsed, and that the light of its explosion was on its way but had not yet arrived. Think about what that window would actually feel like. The neutrino alarm sounds. The physics is unambiguous. Somewhere out there, Betelgeuse has collapsed. But you step outside and look up, and there on the shoulder of Orion is the same soft orange star, apparently unchanged, still glowing quietly as it has your whole life. It is already dead. The message of its death has already reached us, carried by the neutrinos. But the light has not caught up yet, and so the star still appears to be alive, a ghost still shining, and you would stand there in the dark knowing that at any moment, within hours, that quiet orange point would erupt into the brightest star anyone has ever seen. You would be watching a dead star that did not yet know how to look dead. That gap between knowing and seeing, between the neutrinos and the light, is one of the eeriest things physics allows, and it points straight at the strangest fact about Betelgeuse of all, the one we have been circling all night and are finally ready to face. To feel how rare the death of Betelgeuse will be, you have to understand how long it has been since human beings last saw a star explode in our own galaxy. It has been a very long time, so long that no one now alive has ever witnessed it, and neither did their parents, or their grandparents, or any generation for the last 4 centuries. A bright, naked-eye supernova in the Milky Way is one of the rarest spectacles nature offers, and the historical record of them is short enough to list. The most famous one lit up the sky in the year 1054. Astronomers in China and across Asia recorded a new star that appeared in the sky, a guest star as they called it, so brilliant that for weeks it was visible in broad daylight, and then it slowly faded over the following months until it vanished from view. What they were watching was a massive star tearing itself apart, and the expanding wreckage of that explosion is still visible today, nearly 1,000 years later, as a beautiful cloud of glowing gas we now call the Crab Nebula, with a tiny, furiously spinning neutron star at its heart, the crushed remnant of the core. Those ancient astronomers did not know what they were seeing. They only knew that a new light had appeared where none had been, blazed for a season, and gone. The rarity of these events up close is easy to underestimate. Astronomers estimate that a galaxy like ours produces a supernova on the order of a couple of times per century. That might sound frequent enough that we should see them all the time, but the great majority of them go unseen from Earth, hidden behind the thick clouds of gas and dust that fill the flat disk of our galaxy. A star can explode on the far side of the Milky Way, beyond those dark lanes, and its light can be so thoroughly absorbed on the way to us that it never becomes a naked-eye spectacle at all. So the handful of bright, close, historically recorded supernovae are the rare cases that happen near enough and clear enough of the obscuring dust to blaze into our sky. That is part of why the gap since 1604 has stretched so long. It is not that no stars have died in our galaxy in 4 centuries. It is that none of them have died close enough and in a clear enough line of sight to give us the show. The 1987 event is worth returning to, because it is the closest thing to a modern rehearsal we have had. That star exploded not in our own galaxy, but in a small satellite galaxy orbiting nearby, well over 100,000 light-years away, far more distant than Betelgeuse. And yet, even at that enormous range, it became visible to the naked eye as a new point of light in the southern sky, and its neutrinos were caught in detectors deep underground, the first time we ever registered the ghostly particles from a dying star. It gave astronomers a priceless close study and confirmed, in a single stroke, much of the theory of how massive stars die. Now scale that event down across the enormous gulf of distance to Betelgeuse, hundreds of times closer, and you begin to sense what is coming. What was a modest new point of light from 100,000 light-years away would, from Betelgeuse's doorstep distance, become the second sun we have described, a spectacle beyond anything in the historical record. The 1987 supernova was a whisper of what Betelgeuse will one day shout. Then there were two more, close together, near the dawn of the telescope age. In 1572, a brilliant new star appeared and was studied by the astronomer Tycho Brahe, and its sudden arrival helped shake the old belief that the heavens were fixed and unchanging. And in 1604 another one blazed forth, observed by Johannes Kepler, and it too shone bright enough to be seen for months. That one, Kepler's star, was the last supernova witnessed with the naked eye inside our own galaxy. 1604. That is more than 400 years ago. Since then, in all the centuries of modern astronomy, with all our telescopes and all our watching, our galaxy has not shown us another one. We have seen supernovae in other galaxies, distant flickers millions of light-years away, including the one in 1987 whose neutrinos we caught. But a close one, a bright one, a star in our own galaxy blazing into a second sun, has not happened since before there were telescopes to point at it properly. Every astronomer who has ever lived in the modern era has been waiting for one, and none of them has gotten it. This is what makes Betelgeuse so tantalizing and so frustrating. It is, by a wide margin, the best candidate we have for the next nearby supernova, the most likely star to give us the spectacle that no living human has ever seen. It is close, it is massive, it is old, it is visibly restless, and it is genuinely near the end of its life. If any star in our sky is going to hand us the great show, it is this one. And yet, because of everything we have learned tonight, we cannot say whether that show is tonight or 100,000 years away. We are holding the ticket to the rarest event in the sky, and the ticket has no date on it. And when it does finally come, it will leave something behind. The explosion will not simply erase Betelgeuse and leave an empty shoulder, it will leave a remnant. At the very centre, where the core collapsed, there will be a neutron star, that city-sized ball of impossibly dense matter, perhaps spinning rapidly, a tiny fierce object that is all that remains of the giant's heart. And around it, expanding outward for thousands of years, there will be a growing cloud of glowing gas, the scattered outer layers of the star, lit from within, a new nebula blooming in the place where Orion's shoulder used to be. Future generations, centuries and millennia from now, would watch that cloud spread and study it exactly the way we study the Crab Nebula today. The wreckage of the star that our distant descendants would know only as a smudge of light and a story. The ancient orange star that their ancestors once watched die. Betelgeuse would become, in death, a monument to its own explosion, hanging in the sky where a familiar star once was. But all of that, the remnant, the nebula, the monument, assumes the explosion is still to come. And the deepest strangeness of Betelgeuse is that it may not be. The death we keep waiting for may already have happened. We come at last to the strangest fact about Betelgeuse, and it is the one that ties the whole night together. Everything we have talked about, the countdown in the core, the question of when, the waiting for the explosion, all of it rests on a hidden assumption that I have not yet made explicit. The assumption is that the star we are looking at is the star as it is now. It is not. It cannot be. Because Betelgeuse is hundreds of light years away, and light, for all its speed, still takes time to cross that distance. Let me make this concrete, because it is the heart of the matter. When you look at Betelgeuse tonight, the light entering your eye did not leave the star tonight. It left the star hundreds of years ago, somewhere in the range of 500 to 650 years, depending on whose distance measurement you trust. That light has been travelling across the emptiness between the stars the entire time, and it is only arriving now. So the Betelgeuse you see is not the Betelgeuse of this moment. It is a portrait of the star as it was centuries ago, a picture that left home before the telescope was invented, before your country existed in its current form, in an age your history books call ancient. You're not seeing the star. You're seeing an old letter from the star, written centuries back and only now sliding through your mailbox. And here is where that ordinary fact turns into something that can raise the hair on your arms. If the light we see left Betelgeuse centuries ago, then we have no information whatsoever about what the star has done since. Everything that has happened to Betelgeuse in the last 500 or 600 years is still in transit, still crossing the gap, still on its way to us, and not yet arrived. Which means that Betelgeuse could have exploded already. It could have collapsed and detonated and blown itself into a second sun 300 years ago, or 100 years ago, or last century, and we would have no way of knowing, because the light of that explosion has not reached us yet. The star we see glowing quietly on Orion's shoulder tonight might not exist anymore. We might be looking at the light of a ghost, the last calm image of a star that died generations ago, still shining in our sky simply because the news of its death is still on the road. Sit with that, because it is the truest and the eeriest thing I can tell you about this star. When we ask when will Betelgeuse explode, the honest answer is not only that we cannot see the clock in its core, the honest answer is that the explosion might already be centuries into the past, already an accomplished fact, the death flash already racing toward us across the dark, and the quiet orange star we point to on winter nights is a memory, a portrait, a ghost wearing the face of a star that may be long gone. We are not watching Betelgeuse live. We are watching a recording, and we do not know how the story ends because the ending, if it has happened, has not yet reached the screen. And so we arrive back where we began, at the familiar shoulder of the hunter, the soft orange star you have known your whole life without ever saying its name. But it does not feel the same now, does it? At the start of tonight it was a settled thing, a fixed and understood point, one corner of a picture that had looked the same for 40,000 years, and now you know what it really is. It is a bloated, boiling giant that hurls pieces of itself into space. It is a star that hid an entire companion in its glare for 100 years. It is a body spinning at an impossible speed, or perhaps not spinning at all, whose distance and size we cannot pin down, that may have grown to its monstrous form by swallowing another star. It is a countdown we cannot read, running toward an explosion we cannot time, that will one day hang a second sun in our daytime sky, and cast shadows on our ground, and then fade and leave the shoulder of Orion forever empty. And it may, for all we know, already be gone, its death still crossing the centuries toward us. This was the promise I made you at the beginning, and now you can feel the whole weight of it. The more scientists study Betelgeuse, the scarier it gets. Not because it threatens us, because it does not, and never will. But because every answer we pry out of it opens two deeper questions, and because the closer we look at this one bright, familiar, ancient star, the more we understand that we are standing under a sky full of things we have barely begun to know. Watching light that is older than we assume, from objects stranger than we imagine, whose stories may already be over. The fear Betelgeuse gives us is the honest kind. It is not the fear of being harmed. It is the quieter, deeper vertigo of looking up at something you thought you knew, and realizing for the first time how much of the sky is a beautiful guess. So the next time you're outside on a cold, clear night, find the belt and follow it up to the shoulder and look at that soft orange point for a moment. It may be there. It may already be gone, and either way it will not tell you which. That is Betelgeuse. That is the ghost on the shoulder of the hunter, and that is why, the longer we look at it, the more astonishing and the more unsettling it becomes.